test. Not everybody's here, but I am going to, those who are not are just going to miss out on this part of it. I would love to be able to give you a little bit more information than I'm going to be able to give you today. I can give you quite a bit, but, and you don't need to hear about my headaches in creating this test, but I'm trying to do it in as few sections as possible. I would like to, last time we had 4 sections, 2 for each chapter, and I certainly do not want to do that. So I'm trying to merge it into as few documents as I possibly can. And I am finding that because I've created many questions in separate, as separate quizzes, and I wanted to be able to merge them. And I'm discovering that that is not a trivial act on Canvas. Them to try to merge them into one document, they are not in the question bank. So I don't know where they are. They are in hyperspace somewhere. And so I've had to start rewriting those questions to try to create as few documents as possible. It appears at this point that your test will come in 3 sections because I can't rewrite all of the questions. So you're going to have one section that will encompass chapter 3. Variety of questions. Some of them will be true, false. Some of them will be multiple fill in the blank or fill in the blank or things like that. They're very simple questions, or simple to answer at any rate. So that will be one section. There'll be another section also with no math that covers chapters 4 and 5. Nomenclature from chapter 4 will not be included. I'm going to post next week a quiz for you guys to do on nomenclature. You'll see what it's like, and you're going to post a video of you taking a nomenclature quiz on a website that I will provide for you. It's just practice, and you can certainly do multiple attempts at it and submit the best one. So when you get a perfect score, submit it. So you can try it multiple times if you want and videotape the best, but that will be next week. So nomenclature will not be part of it. There will be a third section that is mostly going to cover chapter 3 because it will involve math and upload. There will be some questions there that are short answer questions, but anything that involves mathematics, you're going to have to show me your work, and that will involve an upload. You will not have to upload it as part of that section. You do have to put your mathematical answer into the question, but then you will do a separate upload showing me your work. Obviously, your work has to match your answer. I am going to do the upload differently this time. The upload will be set up as like a 4th part of the exam, and you have to upload your work within 15 minutes of the completion of your exam. So it will not be done as part of the time for the exam. If you are not taking this exam at the regular time, you need to contact me and we need to talk about it, because the computer will identify the time and date that you upload your answers. And I'm going to, excuse me, I'm going to be looking at that to make sure that is within the 15 minutes. So I need to know if you're not taking it for whatever reason, if you have accommodations and are allowed to take it at a different time, you and I need to talk about when you're going to take it so that I know that that upload has been done within the time allotment. Are there any questions about that?
So Professor, for the math section of the quiz, what sort of calculations will we be doing for the math portion?
It will be the kind of things that you did from chapter 3. So you might be calculating frequency from wavelength, or wavelength from frequency. You might be calculating energy transitions, I think. I don't know whether I think there's energy transitions in there, or energy of photons. There's there's a group of questions on calculating the wavelength of a particle. That's the de Broglie equation, things like that. It's all from chapter 3. So make sure you've reviewed the formulas from chapter 3. That's really the only math we've done.
Okay, thank you.
In those chapters. Any other questions? Yes, no?
I have a question, excuse me. So for naming and writing formula, that would be on video quiz, right?
That's going to be on the video quiz when we do it next week. I will post it. I haven't posted it yet, and I'll post it probably by the weekend, but by the end of the week anyway. But right now, as I said, I've been very frustrated with Canvas over the last few days. I literally worked all day yesterday from about 8 o'clock in the morning until 7 o'clock at night, and discovered this morning that the questions I generated are not in my question bank. I don't know where they are, but they're not in my question bank. So this morning I had to rewrite all those questions. It was not a happy camper. It's just I'm finding Canvas and I actually Googled it, and apparently I'm not the only one. It is a thing, and you know, it's like questions just sort of disappear into the Ethernet. So I've had to rewrite a whole bunch of them, and that's why I can't give you a final count. But I think there will be 2 non-math sections, and I still have to work out the timing for those. How long. I did a sample one for the chapter 3 one, and I think it's set up now. I think there's like 15 questions or 14 questions, so I left it at 30 minutes, and I did it in like 10. So I don't think you're going to need 30 minutes for that, but I have to go back over it. And if I think that that's just too much time, I'll try to adjust it so that you have more time on other sections. But I just, at this point, I've been really just trying to group questions in as few documents as possible so that you won't have a lot of my feeling is, and you can tell me if I'm wrong, but my feeling is the more I chop it up into sections and give you time on those sections, the more I'm locking you into not having too much time on one section and not enough time on another. And I don't want to do that. I'm trying to I'm trying to be reasonable about it, but I don't want to have you have 30 minutes on a section that's going to take you 15, and then only have 20 minutes on a section that's going to take you 30, because that doesn't make any sense. So I have to get the questions grouped, because the quizzes will be submitted at the end of the time limit. And if you're not finished, you're going to take zeros on questions that you might know how to answer. So I really don't want to have the timing become an issue for you. And that's why I'm trying to put it in as few documents. I'd rather have one document where you have 40 or 45 minutes than have a whole bunch of shorter documents. So that's what I'm trying to do at this point. But it's not trivial. So, any other questions? Excuse me.
Were the test questions at all formed around the textbook practice problems? Because I know when I do the textbook practice problems, they give me, I don't want to say like extra stuff, but they get a little weird and funky.
I can't say that they are, and in all honesty, I have not written all of them. I've written some of them. And I can tell you that the one you probably have seen, because I write the quiz questions as well. So I don't think I've written anything that's tricky. The ones that have been written by my colleagues, there was one that I deleted. I chose not to use because it's not something that we emphasized in class. And while the book covered it, I didn't feel that it was fair to ask you that question since I didn't cover it much in class. So I took that one out. But so I don't think any of them are particularly tricky.
Maybe we know which one that was.
No, it was just it was on nodes. And I talked about nodes, but I didn't spend a lot of time on it, and I know the book covers it, but I just didn't. To me, that wasn't that important, so I took that question out. I actually, to be perfectly honest, I don't ever look at your books questions, so I don't really know what they're like. But I know that. Well, I have questions that have probably been written by two other people, two other of my colleagues. One of them, Dr. Meyer, I have worked with. I've known him for 20 years, and I know how he writes a question, and he never tailors his questions to the way the book writes questions.
Excuse me, Professor.
Mm-hmm.
For the third section about math,
Yeah.
you say it's mostly on chapter 3. Can you give us the estimate, like how many questions it's going to be on
No,
that
'cause
section? Oh, okay.
I mean, at this point, I don't even know. I don't even think it has a time scheduled on it, and I have to. And that's the thing. I have to figure out how much time the other sections are going to take. And then I'll figure out how much time that I have for that and whether I can add any questions to it. I don't think there will be some short answer questions too. There'll be some questions that do not involve math. But they happen to get put in that section. And let me I'm going to make a statement right now. When we write a question, we have different categories we can put them in. And one of those categories is essay. They don't have anything called short answer. It's either essay or fill in the blank or whatever. And one of the things that I discovered for some of you in the last test is that if I do it as fill in the blank, it is very limited to how many words or letters you can type in there. I was expecting you to type in an answer that was fairly short, and some of you were typing in an explanation. And as a result, your explanation filled up the box, and in some cases, I couldn't even see what your answer was because I only could see the first part of your explanation, and your explanation appeared to be right. So I assumed your answer was right, and I gave you credit for the question, even though I couldn't see the answer. So that led me to the conclusion that if I want you to write any kind of an explanation for something, I have to give you an essay question. I want you all to understand that essays in chemistry, in general, mean short answer explanations. If you can't answer that question in 3 sentences or less, you're writing too much. You're writing too much and you're not organizing your thoughts. You really should not have to use more than 3 sentences. I remember taking a graduate class in biology. In biology, most of you will remember from your past biology classes that there's a lot more essay kind of questions in biology. And I remember in a graduate class being told by my graduate professor, you should be able to answer this in 10 sentences or less. I am going to stop reading after 10 sentences. So if you haven't answered it in the first 10 sentences, you're not going to get credit for it. And I would say the same thing is true for chemistry, except that it's even fewer sentences. So when I say there are essay questions, you're going to be explaining why something occurs, explaining why a trend occurs, or explaining why something is incorrect. If you're given something that's incorrect, you might have to explain why it is incorrect. You ought to be able to do that in just a couple of sentences. And, but those will be, I think there will be some of those on the third section of the exam that includes some math. You don't have to do an upload from that, of that. You'll be writing that on in the test. The upload will be just for your math work. Okay. Okay, I think we're probably ready to go ahead. And so I am going to start chapter 6. Okay. Okay, so we're actually going back to some quantitative math, at quantitative chemistry at this point. We have done some of this before, so this isn't brand new, but we're going to expand on what we've done. We're talking about, among other things, the composition not just of substances, but also of solutions. So we've talked before about how to calculate the molar mass of a compound. For a molecular compound or covalent compound, it will be the molar mass or molecular mass. It's obtained by summing the masses of all of the constituent atoms. By the way, I did want to point out something here. This came up, and this relates this to the work that we did in the last chapter. This molecule is chloroform, CHCl3. And one of the caveats I told you in determining whether a shape was polar or not was whether the molecule was symmetrical, but whether the bonds were polar. And one of the things I said in a couple of questions people had was, the assumption is the central atom is bonded to all of the same constituent atoms. This is chloroform, and it has 1 bond here to hydrogen and 3 to chlorines. If this was carbon tetrachloride, in other words, if this was another chlorine, even though those bonds are very polar, the molecule itself, due to its symmetry, would not be polar. The fact that we have a hydrogen here instead of a chlorine means that this molecule, in spite of its symmetry, as far as the electron pair geometry goes, is going to be a polar molecule. So I just wanted to point that out. I did, in discussing with a couple of people, say, assuming that the bonds are all to the same atom, a symmetrical molecule will not be polar. And this is an example of that assumption. So in this molecule, you have 1 carbon, 1 hydrogen, and 3 chlorines. So you take the average atomic mass of each of those, and the molecular mass is 119.37. when you're talking about ionic substances, they exist in these large three-dimensional arrays. They go out in three-dimensional space. And so there is no such thing as an isolated molecule. So what we do is, in this case, we're going to talk about the formula mass, and the formula mass is determined by the simplest whole number ratio that exists in that compound. So this is aluminum sulfate, and the formula is over here, Al2, SO4 taken 3 times, or 3 sulfates. So we multiply aluminum by 2, sulfur 3 times 4 is 12. Excuse me, 3 times, sulfur is 3 and oxygen is 3 times 4 or 12. So 12 oxygens and a total of 342.14. So very quickly, there's I'm going to put you guys in breakout rooms just to do a little practice. This is going to be a short one. You're going to have a number of breakout room sessions today. So this will be a real quick one to give you some practice calculating molar mass or formula mass. So if you did not get it finished, hopefully you'll be working together on this and maybe sharing information. But you do have to post it if you want to get credit for it. They are graded, and it's just graded for extra credit. The second thing you should have seen by that is that there will be times when you're given a name and you're going to have to produce a formula. So obviously that's why we did that exercise of practicing writing names and formulas. Okay, so let's go back to this. Okay, so we just talked about molecular mass, but for the most part, since you're not going to be working with individual molecules, you'll be working with large populations of molecules. We will reinstate our relationship between molecules and moles of molecules. Going big changes very little. Numerically, the mass in AMUs per molecule is the same as grams per mole. They're the exact same values. We covered that in an earlier chapter. So what can you do with molar mass? Molar mass is a conversion factor between grams and moles. For the most part, I'll tell students when you're given a problem in chemistry, if you're given a mass, the very first thing you should do is convert that mass to numbers of moles. That's the very first thing you should do. Even if you have no idea right off the bat of how to approach the problem, that's something that you can do as a start. I also am going to say that one of the things students always ask me, when I ask you to show me work, I'm not going to expect you to show me how you calculated the molar mass or the formula mass. The assumption is that you're going to know how to do that, and you'll be able to use that mass in whatever calculations you need as a conversion factor. If you make a mistake, then you'll get 1 point off for a math error. But if the rest of your process is correct, then that's the only point you'll lose. So you don't have to show me how that's not part of the work that you have to show me, how you calculated the molar mass. So we have done this kind of a conversion factor before by taking the mass and dividing it by the molar mass, you figure out how many moles. We've also used Avogadro's number to get to numbers of particles. We're now going to introduce another factor because we're sometimes going to be talking about substances that are dissolved in solvent, usually water. And we are going to use density in grams per milliliter, or in the cases of gases, it may be grams per liter, but we'll use the density and the volume that will allow us to calculate the mass. Volume times density will equal mass. So that's another conversion factor that you're going to be able to use. So I have a couple of problems here that I am going to work out for you because I think sometimes it helps. for me to show you how I do the problems, and then you're going to do some practice. So let me switch to this. Okay. So that first problem was the density of benzene, C6H6, is 0.86 grams per milliliter. How many moles of benzene are there in 1.22 milliliters? So we're going to take the volume, 1.22 milliliters, and we multiply that times the density, which is 0.876 grams per milliliter. And then we're going to multiply that by the molar mass, because we want to know how many moles we have. So 1 mole is equal to 78 point, what did I calculate it as? 78.108 grams per mole. So milliliters will cancel, grams will cancel, and we end up with 0.137 moles. Now I'm going to do that math for you because I want you to see 1.22 milliliters times 0.876 and divide that by 78.108. What I get off my calculator, if you can see that, is 0.01. I'm missing a 0. 1.22 times 8.876 divided by 78. Yep, there's a 0 missing. There we go. You'll notice that it's going to give me a very long number, but I am limited to 3 sig figs because my initial volume measurement was 3 sig figs. I also have 3 sig figs in the density, but this might be more variable. I have more digits in the molar mass, but your real measurement, your real limit is going to be in the measurement that you took, which was 1.22 milliliters. Now, the second question that we have is, what is the volume of 9.4 times 10 to the 22 molecules of chloroform? And I've given you the density of chloroform is 1.492. So here we're starting on the other end molecules and we're working backwards. So we have 9.4 times 10 to the 22 molecules times 1 mole is 6.022 times 10 to the 23rd molecules. And we multiply that by the molar mass of 119.37 grams per 1 mole. And we also multiply that by the density. The density is 1 milliliter is 1.492 grams. Notice that normally you think of density as grams per milliliter, but it is a conversion factor that can be written in either orientation: grams on top, milliliters on the bottom, or milliliters on top, grams on the bottom, depending upon which direction you're going in. I always like to check molecules cancels, moles cancels, grams cancels, and that is going to leave me in a final unit of milliliters, which is what I wanted. So 9.4 times 10 to the 22nd divided by, divided by 6.022 times 10 to the 23rd times 119.37, which is our molar mass, divided by 1.492. And I end up with 12.488, but I have to limit myself to 2 significant digits. You don't have to go beyond the 4. You don't have to go to that 8. That 8 would make that a 5 and da, da, da. You just go to the next digit. It's 12.4. 4 is less than 5. So your answer is 12 milliliters. And that's the answer. So that's the answer for that one. So that's going in both directions. We've just added a new conversion factor using density because we're going to be working in volumes. So I'm going to ask you to go to the breakout room and do the very next discussion. Let me double check what it's
Professor,
called.
I just have a question before
Yeah.
I go.
Sure.
So what is the difference between mole with the E and without the E? Those are two different, like,
No. They are actually the same. Somewhere along the line, somebody decided that a good abbreviation for mole, M-O-L-E, was M-O-L. It doesn't seem like much of an abbreviation, but it's just the abbreviation for moles.
okay, it's make me confused a lot of times.
Yeah, no,
Yeah.
it just means moles.
All right, thank you.
Yeah. It's always given to you as part of every test. Because we're testing online, if I were giving you a paper test, I would include a periodic table with that paper test. I'm not giving you a paper test. We're testing virtually. What I will do is the same thing I did the last time. If you would like, you can open up the periodic table that's in the appendix to your text. I can also open that up and share it on my screen during your test. I'm happy to do that if you don't want to keep going back and forth to that. But yes, you absolutely have to have a periodic table with you, and you will for the rest of the semester. So let's go back. So we just oh, I didn't get it. So this is where we were. Okay, so one way to assess compounds is through percent composition. How much of each, how much of the total mass of the compound is made up by the masses of each of the individual elements. That's the percent composition. So the mass of each component in the compound compared to the total mass. So here's an example of, for ammonia, whoops, I'm sorry. Didn't need to do that. I want to go to the wrong one. There we go. And the mass of 1 mole is 17.034 grams. So nitrogen, there's 1 nitrogen, its molar mass is 14.01. So 14.01 grams of this total is nitrogen. There are 3 hydrogens, each has a mass, each mole has a mass of 1.008. So 3.028 grams of this total is hydrogen. So we simply take the mass of each constituent element divided by the total times 100, part over the whole times 100, tells you that 82.25% of ammonia is comprised of nitrogen, 17.75% is hydrogen. Here's another practice problem. Aspirin is a compound with a molecular formula of C9H8O4. What is its mass percent? We start with the mass of carbon times, I'm going to change this now to a pen here. Let's do it here. Each 12.09, excuse me, 12.01 grams times 9 is equal to 108.09 grams. That's how much it would be carbon. 8 times 1.008 is 8. Oops, I'm sorry. There we go. Equals 8.064 grams. And 16 grams for oxygen times 4 of them is equal to 64 grams. This would be in 1 mole. And we'd simply divide that by the total. You'd simply add those 3 together to get the total. It's 180.154 grams is the total. So part over the whole times 100 would give you, I'll simply say that when you do the math, that's 60% carbon. 8 grams out of 180 times 100 is 4.5% hydrogen, and 64 divided by 180.154 times 100 is 35.5%.
So you just multiply. Wait, what exactly are you?
What I'm doing, I'll show you for carbon. I took 108.09 grams divided by 180.154. This is the mass of carbon divided by the total mass.
Okay.
Okay, times 100 equals the percentage.
Oh.
Okay, so that's how you get the mass percent. So this is the composition for aspirin. Aspirin is 60% carbon, 4.5% hydrogen, and 35.5% oxygen.
Okay.
When you add them together, sometimes when you do it this way, sometimes you'll find when you add these together, it doesn't quite add up to 100. It should add up to close. It might add up to 99.9%. It might add up to 100.5%. So it's going to be around 100%. The difference is rounding errors. Notice these answers down here show 60%, 4.476, 35.53. These are not necessarily appropriate significant digits. So when you round to the appropriate number of significant digits, you will sometimes find that when you add it up, it's very slightly more than 100 or very slightly less. That's okay. Those are just simply rounding variations, and it's okay. So empirical formulas, the most common approach to determining a compound's molecular formula is to first measure the masses of its constituent elements. If I'm a synthetic chemist and I create a new compound, or I think I've created a new compound, the very first step that I'm going to take in trying to figure out what that compound looks like, if you want to know what the second and the third and the fourth steps are, you'd have to take organic chemistry. But the very first step I'm going to do is potentially try to discover what its composition is based on mass percent. What I'm doing there is only calculating empirical formulas. I cannot get the molecular formula. The most common approach is to first measure those constituent masses, but this represents relative numbers or moles, not the masses of the atoms. So one thing that you can do if you are given a percent, if you're told, like in this last slide, if you were given these percentages down here and asked to measure the empirical formula from that, you can work backwards by assuming that you have 100 grams of your compound. If you have 100 grams, then those percents become masses. So 60% carbon would be 60 grams of carbon. That would be the mass that you would start with over here. And then you would divide by the molar mass to determine how many moles that was. 4.5% hydrogen would mean that the compound had 4.5 grams of hydrogen. And so you do that for each of the constituent atoms, and you end up with moles of atoms. And that's going to give you the ratio of atoms in the compound. The problem is it might not give you the whole numbers. So if it doesn't give you whole numbers, you can't have half an atom. So you have to get it to whole numbers. And the first step in doing that is to divide by the lowest number. That's going to guarantee that one of those constituent elements is going to be a 1. You divide by the smallest, that turns that one to 1, and then you look to see if the rest have become whole numbers. If they haven't, you might have a ratio of 1.5 or 2.5 or 1 1/3. In that case, you can multiply by a number to convert that to lowest whole number ratio, and that will give you the empirical formula. So let's do a practice problem. These are the 2 practice problems that I'm going to do for you. So let me shift my camera. Okay. So that first one was an oxide of iron found in many iron ores, contains 34.97 grams of iron and 15.03 grams of oxygen. I want to know what the empirical formula is. So I'm going to take 34.97 grams of iron, and I will multiply that by, or actually I'm dividing it by, but I'm going to multiply it by the factor 1 mole is 55.85 grams. That's the molar mass of iron. And that equals 0.6261 moles of Fe. Then I have another element is 15.03 grams of oxygen. 1 mole of oxygen is 16 grams. When I provide that, perform that division, I end up with 0.9394 moles of oxygen. Now, I look at those 2 numbers, that actually gives me, this is the formula that I get from that, Fe 0.6261, O 0.9394. That obviously can't be my molecular formula because I can't have fractional atoms. So I'm going to divide by the smallest. I'm going to divide by 0.6261. That automatically converts that to 1. So Fe1, I'll put the 1 in there for now. You don't need to put the 1 in. When I divide 0.9394 by this number, I end up with O 1.5. So I've improved my fractions a little bit, but I still don't have whole numbers. But I notice that this is actually 3/2. So I can multiply this whole thing by 2 to clear that fraction. And that gives me Fe2O3. You have to learn to recognize common fractions. Usually it will be either a half or a multiple of a half, or it'll be a third. Occasionally it'll be a quarter. Usually not any worse than that though. So you might have to multiply by 2 or by 3 or by 4 to clear whatever fraction you have there. Does that make sense to everybody? I see one nodding head and lots of black squares, so I will move on to the next one. Okay, so most of you are just allowing Amit to let you to pass on whether you're understanding this or not. Okay, so the next one that I have is, what is the empirical formula of a compound containing 40% carbon, 6.71% hydrogen, and 53.28% oxygen? If you add that, as I said, notice if you add those together, you'll find that it doesn't quite add to 100%, but it's within rounding errors, it's fine. So I'm going to assume, yes. You had a question?
Can you go back to the first one real quick?
This one?
Yeah, thank you.
Oh, you copying it down? Is that what you're doing?
Yes.
Okay.
I actually have a question, Professor.
Sure.
So why do you like multiple it by 2 but not by any numbers?
Because I have, in this formula, when I divide by the lowest number, I end up with 1 iron and 1.5 oxygens in the formula. I can't have a half an oxygen atom. I
Right.
have to have whole numbers of atoms. So somehow I have to make this into a whole number ratio. And I can clear that 1.5 most easily by multiplying it by 2 and
Mhm.
making it 3. So it's Fe2, but I have to multiply the whole formula. Can't just multiply this.
Right.
I have to multiply the whole formula. So it becomes Fe2O3.
Okay.
Okay?
Makes sense.
Okay. Ready to go on? Jonathan? Was that-
Yes.
Oh, okay.
Yes.
Okay. All right. So in this case, the last one I was given masses. In this case, I'm not given masses, I'm given percents. But as I said, I can always assume, and I would always, when I was a student, I would always say, if you're making an assumption, your professor needs to know that you're making an assumption. Okay. And so I would simply say, assume 100 grams. And then I would do the problem below that. All right. So that means that the percents become masses. So I have 40 grams of carbon, which I multiply by the molar mass, or the conversion factor including molar mass, which is 1 mole is 12.01 grams. And that's going to give me 3.33 moles of carbon. I have 6.71 grams of hydrogen. 1 mole of hydrogen is 1.008 grams. That means that I have 6.656 moles of hydrogen. And I have 53.28 grams of oxygen. 1 mole of oxygen is 16 grams. That comes to 3.33 moles of oxygen. Okay. You can already see that you have an equal number of moles of oxygen and carbon. And that's the smallest number. So we're going to divide by 3.33. And when we do that, we end up with CH2O. And that is our whole number ratio. We don't have to multiply by anything this time. It comes out in a whole number ratio. So that's the empirical formula for this compound. Okay. Okay. So I think, if I'm not mistaken, there is probably, let's go back. Oops, I want to share my screen. Okay, so that's the 2 practice problems we did, and I think there is a breakout room session for you. So let's see. Yes. Here is let me go back to sharing my slideshow for a second, because this breakout room, I'm going to show you the instructions on this breakout room here. They're slightly different because they were written actually for an in-class, but I want you guys to do your own practice. I want you each to write a formula for an ionic compound that contains a polyatomic ion. You can choose any polyatomic ion you want. You can choose any metal you want. Create the compound in a balanced formula. Determine the percent composition of its elements by mass, which is what we've just been doing. In class, I would ask you to do it this way. I would ask you to write the formula of the compound on one side of an index card and your results for its percent composition on the back. But I want you to create a compound and I want you to give it to somebody else in your practice room. And I want them to solve your problem and check their answer with you. And I want you to solve their problem as well. So the instructions are written in the breakout room on the discussion. So create compounds for each other. If you really want to test them, ask them the name of it.